So, and we're being recorded. Didn't come to us from SDSCI, where she's an associate astronomer with tenure. Her path went through Columbia and the High State University, where she got her PhD in 2004. She went through several postdoctoral programs, UC Santa Cruz, IAP in Paris, Oxford, and then Conrad, where she did her FPP before going to SDSCI. And she's an expert in many things. She was telling me a long list just before the talk. Today she's going to talk a lot about kinematics, but she does outflows, she does galaxy dynamics and assembly. And yeah, so I'm really looking forward to hearing what she has to say about JWST. Take it away.
You guys have a pointer?
There's one right behind you.
There's a big stick behind you.
But please don't speak softly.
Let me know if you stop hearing me or whatever. So thank you.
Making a joke about speak softly and carry a big stick.
Once before a talk, they told me, "All right, honey, don't cry." That was the best moment. So thank you for having me. Thank you, Kirk. It's really been a pleasure getting to know you all, and thank you to your admin, Daniel, for helping me with so much logistically. And it's really, you guys are a wonderful, wonderful department, and it has really been a joy getting to know you all and to see some of you again. So I'll be talking, this is a nearby image of a nearby disk galaxy. Our nearby disk galaxies are beautiful. They're symmetric, they're thin, and they're rotationally supported against collapse. The stars and gas are in circular motions around their centers. They have mature structures like spiral arms and bars, thick and thin disks, dust lanes, and all that jazz. So I'm going to briefly talk about observations, kind of older work of mine showing how these galaxies spin up and increase in angular momentum with time for more disordered progenitors. And then I'm going to spend most of the time showing you some recent results from a James Webb program that we did that are not published. So, this is interactive. And again, this is a new talk, so please feel free to interrupt and tell me I lost you or I need to clarify or you have a question. And if I'm going too fast, also tell me. So, because I have not metered this talk yet. So when we're going to talk about when do disk galaxies obtain their current well-ordered state? And also, what is the dynamical state of galaxies in the distant universe? So these are two questions to think about during the talk. Now, this is the teaching slide, and try to keep this in mind throughout the talk, because we're going to be looking at velocity maps a lot. And if you don't get this one, it's going to make your life miserable. So this is a rotating disk galaxy in the local universe. It's beautiful. It has an NGC number. It has a beautiful bulge here, these wonderful spiral arms coming out, structural regions throughout. Here's a FabiPro H alpha map of that galaxy, showing that it rotates. You see the blue coming toward us at 200 kilometers per second. And the red part, the other side of it, going away from us at 200 kilometers per second. It's in a disk and it rotates. It has some inclination to the line of sight. That's why you see it. You can see a bit of its face there. And this is measured from, the velocity map is measured from the H alpha nebular emission line, which traces gas in the galaxy. Kind of warm 10 to the 4K nebular gas. Another quantity we measure that's measured for galaxy kinematics is not just the rotation velocity, but at every point in here, what the velocity dispersion is, or what the range of velocities are at that point. And a disk like this rotates, massive disk rotates at plus or minus 200 kilometers per second, and has a bubbling of their H2 regions here, this velocity dispersion of about, on average, 30 kilometers per second.
And that's still within the H2 region, so is that, so that's in the gas itself?
in the gas
So is it like
itself.
turbulent motion? What's the origin of the dispersion?
I'm not sure. I think it can be, it's probably just the bubbling around, just being in a disk, just gravity, it's thermal motions.
Yeah.
Yeah. As you'll see, I think galaxies, there are theories that are not published. My colleagues are working on this, show regulatory mechanisms, even in the simulations, where they tend to form these disks and they thin out over time. They're trying to match some observations I'll show you in a minute that we were just weirded out by. But I'm going to go through them fast. Okay. So we know that galaxies get weirder as you go. We're weirder back in time. So this is redshift 4, redshift 3, redshift 2 to 0. And then they look normal in time. So we want to trace how the kinematics evolve to where we get to these disks today. So here's the plot many of you know and love of look back time versus redshift. Just to remind everyone, from 0 to 1, 8 billion years. From 1 to 2, 10 billion years. Gigayear means billion years, 10 to the 9. So I'm going to breeze through this because it's older work. And I'd like to focus on some more new stuff. But what we did is we measured rotation velocity and then integrated an average gas velocity dispersion for galaxies spanning from 0 to 2 in redshift. And we were the first to really measure this gas velocity dispersion and do the corrections properly for seeing. And we found kind of essentially 3 classes of galaxies. One that's rotation dominated. You get these kind of disks. These are 3 galaxies at redshift 1, and it rotates. Has a velocity dispersion, but it rotates. This one, I don't know what it is, but it's that the emission line is fat. It has a lot of velocities at a given location. And this one is mixed. It is a bit of both. It rotates and it has that velocity dispersion. And what we found is that the velocity dispersion, and a key part of this was actually going to simulations and being like, is this real? Do you also see this? And we use merger simulations for that in Covington. Does the sigma, we found that sigma gas, it integrates over velocity gradients on scales beneath the seeing. The seeing is essentially the blurring in the atmosphere, which is like, this is what it was here. And it quantifies the amount of disordered motions in galaxies. Yes.
So what does seeing mean in the context of a Hubble Space Telescope image?
Yeah, I'm showing you, this is where I'm breezing through stuff. I'm not showing you the spectrum. So the Hubble Space Telescope is not affected by seeing.
Right.
But we did, I apologize, all spectra of high redshift galaxies, I made an assumption, did not come from Hubble. It came from 10 meter class telescopes.
Okay.
So we did, I told out slides. So this is a stop of, thank you.
Okay.
So we measured
Hubble, but the velocities are from the spectrum.
from ground base, it's from Keck, from 10 meter class telescopes. And so we were affected by seeing, which actually being a good thing because it actually integrated velocity dispersion for us. Otherwise it would have been a crazy looking map. We would have just put our hands in the air. And what we found is that it quantifies the amount of disordered motions in galaxies. And once you take V-rho and sigma and you put them together in a dynamical quantity that adds them properly together to trace the total dynamical mass in galaxies, you get a tight Tully-Fisher, which is magic. You're not worried about, do I put it on Tully? Do I plot it on the plot? Do I not? You get a tight one no matter what. And it's coincident with Faber-Jackson. That's old 2007 work. So we found that was really important. And we found that essentially you need both of them to trace the dynamical mass of the galaxy at these redshifts. Then we looked at velocity versus redshift and velocity dispersion versus redshift for hundreds of galaxies. And that's what these little points are in the background. So there's a lot of scatter, but then when you look at the medians of these points, which are these giant points meant to draw your eye, you start to see trends. And we called this disk settling. It's in this 2012 paper, and it pushed it out to redshift 2 in this 2017 paper with my student, Raymond Simons. And what you see is that with time goes from here to here, you see galaxies spinning up, especially at lower mass, or increasing in rotation velocity. And here, this is really shocking, this velocity dispersion goes way down and it's independent of stellar mass. So stellar mass is higher in the red and lower in the blue. And this has since been reproduced by many of surveys. So it's kind of nice. We call it dissettling. How does the fraction of disks evolve with time? So let's take these two numbers that we have, because we had ground-based. So we were just blurred. We had single slit. We had two numbers. We said, okay, let's assume, let's say, okay, what is a disk in terms of these two numbers? Well, in the local universe, the Beard over sigma of like the NGC 7171 I showed you is like 10. But nothing reaches that at higher redshift. So I was like, I don't know, 3, which is like a low mass poopy guy. So let's look at this. So what's the fraction of like all the star-forming galaxies in our survey? It's like 200 galaxies. 500, 600 maybe, greater than 3 versus redshift. And so divided into mass spin. So what you see is that all the lines go in this direction. You always see increased fraction of disk with time. And then this is essentially downsizing that higher mass things form first. So for the students, you know, galaxies evolve with time. They also evolve with mass. The higher mass ones are the most evolved. That's that downsizing thing that we did. And yes.
I have a question. So
Yeah.
when you say the velocity dispersion of the gas, you mean like the peak velocity dispersion in the kinematic map?
The average,
Yeah.
there is no map on these. We averaged over it.
Okay.
Yeah. And then what people do when they get the map, they take an average,
Okay.
but not the peak. The peak is due to the rise in rotation curve. You have to model that properly. That's where you need to model the seeing.
Okay.
Yeah. Old papers didn't model the seeing. Keep that in mind. We did, and then we started seeing stuff. Because we'll talk later, but that's a subtlety I didn't want to drag into this talk. So yes,
So is the rotation velocity measured when the rotation curve is flat?
it's as close as it's an upper limit. It's close to be flat as we can make it. Some of them don't fully turn over. So it's like a lower limit to it. But most of them hit B flat or approximately at B flat. We went pretty deep. So it's not advancing. Ah, there we go. And just to keep you in mind how low these fractions are, it's 30% high mass at redshift 2 and change. Then Webb was launched January 2021. For this field, at least it enables higher spatial resolution. You're not using these 10-meter class telescopes with seeing, significantly increased sensitivity and hot studies at higher redshifts. Because it goes into the infrared. I'm not going to belabor this. It's pretty cool. That's why I took the job there. And it's a national facility that everyone can apply for time on, and I encourage you to, and let me know if you have any questions about your proposals. So one of the many modes on James Webb is called the micro shutter array. It's a multi-object spectrograph, which is fancy for saying it can do more than one object at once. It can get spectra for a lot of stuff. So what it is a screen, essentially a screen grid. Here it is in the lab. With these little shutters that you can open and close to create slits on top of galaxies. And you can do many galaxies at once, hundreds to thousands if you want to let them overlap. Over 3.5 square arc minutes on this side. So here's just an image of a deep field. This little box here is zoomed in here, and this little box is zoomed in here. This is just an example observing program with the micro shutter array, where the observer opened these little McDonald's colored shutters on objects, and they're going to get the spectra out and analyze them. Yes.
Would I ever want to just open all the shutters? I mean, why would I ever want to close any?
Because you get spectra to overlap. There's a program led by Matthew Case that opens them all. It broke all of our software, but he's happy with the results.
Good. Or I guess if you had a bright star in the background.
That too, but overlapping spectra, it depends on the science you want to do. Like say you're just interested in one emission line, yeah, let them overlap. Why not? Yeah. So I'll be talking about the Garden Survey, which is a program we did on James Webb. I'd like to highlight Camilla Pacifici, students Celia and Ezra, Celia Mulcahy and Ezra Suquet, you'll be hearing about their work. Jane Morrison, who did, and Eddie Bergeron and Mike Reagan, who helped a lot with the tremendous infrastructure on this program. It helps to work with the best. So we decided to use the MSA in a creative manner. Rather than just getting one slit per galaxy, we kind of wanted to get the map. As you saw earlier, it's kind of useful. And so one thing we did is, so you take the shutter, and let's say you move it along the galaxies. We did 6 times. And then for galaxies that are smaller and generally fainter, you just observe, you don't have to do as many steps, but you observe some of those steps multiple times. And you get to the limit where you have some galaxies that are 1 step and observe multiple times. You can get crazy with this, but it's basically a lot more efficient than using another mode on our telescope. So this is 3.5 arc minutes on the side, this MSA, whereas the IFU is 3 arc seconds on the side. So it's shooting 1 by 1. The data reduction is a heck of a lot easier though. So it's more efficient to do the survey mode for my science. And then we also, for the aficionados, the observers, we did a nice dither, 5-point dither pattern at each step. So we called this slitlet stepping. I named it after an old IFU dither pattern, and it kind of stuck. Be careful what you do when you first name something. It's a weird name. We did 56 galaxies between redshifts 1 and 6. We did the highest resolution on Webb, which is R3000, giving you 1.5 to 3 micron spectra. We did 10 hours per step, 60 hours on source. So when you do this, we knew we were going to open a Pandora's box. We're going to push things to the limit. So I was able to contact people who work on detectors in my institute and work very closely with them. And you'll see their work in a bit, Mike and Eddie. We found a lot of stuff too and dug it out. So if you did it with an IFU on Webb, it would take you about 4 months or more. So Garden is deeper than most surveys, but it also has a lot fewer galaxies. It's really a pilot to see what are you going to get. I like taking a telescope and just driving it hard. And with these kind of surveys, we're looking at luminosity functions, mass functions, other stuff. We have another program that is hundreds of galaxies that's getting at some different questions. I want to highlight the work of Jane Morrison, one of the astronomers on the program at University of Arizona, who wrote the cube building software. It takes the spectra and dithers them onto the sky and gives us these drizzled cubes. It's not easy, but Jane is a genius. So we were able to do this. And it uses the JWST data models and the WCS of the slits. Yes.
I don't understand what drizzled means.
I'm
Why is
sorry.
it on the
I live in a box.
course? No.
No. I'm using terminology that we use a lot at the
Weird.
institute because it's just so, we use acronyms and stuff. So when you have, let's say drizzled is, I don't know, it's just, but imagine you have multiple images of me taken at different points and all the pixels are like see you had in your camera, a lot of pixels, but they overlap sometimes. Like you're not taking it in the same location, so you're moving those pixels around on my face. Imagine you want to combine them, but you can't just take a pixel and just add all the pixels there because you moved it around, you dithered. You're going to count the fraction of one of the pixels that was in this. You take a pixel, a drop pixel, and you count the fraction of all the little pixels that landed in it, and you kind of combine it in a cool way. Jane did this in 3D. Yeah, so you take the spectrum, they all have a dither pattern, they all overlap, and then you dither them onto the sky using the WCS and the data model. And she backed out problems too while she did this. It helped us debug stuff because Webb wasn't meant to do this. We found cool stuff. Mike and Eddie were fundamental in this, powering through all the cosmic rays. Leave-in cosmic rays, persistence. I can bore you with all this, but it's actually quite exciting. We identified that your position was wrong that it gave you with the MSA. It forgot to add in another offset. that it did. We dug that out and had a little celebration of exhaustion when it was figured out by the team. But that will be added into the pipeline in the future. So where your slit is with the MSA is a little wrong. Talk to me. Yes?
So what's snowball lingo? What is that?
Oh God, again, lingo. See, I have to remember the lingo for talking. That is when you have a cosmic ray hitting the detector and having a little shower. It's not pretty. It's one of the first things we notice. Wow. So you're setting cosmic rays, shouldn't you? Yes.
Yeah, I'm not sure about the high res grading, but for prism, I think it is noticed that the wavelength calibration is not perfect.
No, it's not.
Yeah, so have you like tried to correct the wavelength calibration?
Yeah, oh no, not so much for us. We haven't done that yet, but for Prism, I haven't touched the Prism data.
Uh-huh.
Yeah, we haven't worried about this because we've been doing one line at a time, but yeah, that's something that's on our list. But we wanted to get these detector things in first. Yeah.
And for individual like slit spectra, have you tried to extract the spatial information along the slit direction?
Absolutely. That's what a lot of the cube does.
Uh-huh.
Yeah. Yeah, if you have stuff, tell the institute you have a problem with it by putting it in a help desk ticket and they just count how many are there and then they decide what to work on.
And then for the spectral within the slitlet,
Mhm.
there are still like some spatial information.
Oh,
about
that's
the slit.
what we do. That's
Uh-huh.
what this is here.
Okay.
Absolutely. There's
Cool.
for each shutter, there's 4 pixels this way, 2 pixels this way.
Yeah.
That's what Jane did with the dithering. Yeah, she took that all into account. You got it. You're thinking along the right direction. And that's a pun. So, you know, because the team, I was on the NIRSpec team for years, is just so overwhelmed. You know, we're doing this on our own and kind of giving it to them if they're interested. And but if the institute, if you guys are interested in any of these corrections, do contact me. They help push the spectra much deeper. Here are these spectra. This is a nice plot that Eddie made. He just took a white light image, but applied R, G, and B colors to different, just like to different regions of the spectrum. So the bluest part is set to blue, the reddest part is set to red, and the rest is green. And you see all kinds of like artifacts that we dealt with. That's a short that just shows so brightly. But you know, even overlapping spectra we can take out. There's this dynamical background hanging out in there. It has a lot of features in it. It's cool. So this is one galaxy we'll be talking about at redshift 2. And here's another one. It has we took out that green net madness there. It's overlapping spectra. Which is the hard thing to do. Now we're going to look at 2 galaxies in detail. So join me on this tale. This has been fun. We didn't get beyond these 2 galaxies for a while. We chose them to be major mergers because of these Hubble images. This is work done with 2 amazing grad students, Celia Mulcahy and Ezra Suke. They're at Johns Hopkins University. They will be applying for jobs in fall fall in 27. So first we're going to talk about what I call the bear claw galaxy because it looks like the Panera pastry. It's a massive star-forming galaxy. We thought it was a merger, and then we got the Hubble image and the James Webb image from NIRCam. We're like, oh my God, it has this dust enshrouded kind of bulge in there with these beautiful spiral arms. So I'm a big fan of going deep on a few to understand what they're doing and then applying that knowledge to a larger survey that's maybe not as deep. But here we are. Oops, the image. This is the rotation velocity map of the galaxy measured from H alpha emission lines again. Red means it's moving away from us. 300 kilometers per second, fast guy. Here it's going toward us. Maybe I got the number, the sign wrong with it, but that's at 300 to 300 kilometers per second. Also, what's very interesting here is the velocity dispersion map, showing a peak at the center due to the rise in the rotation curve, as you pointed out. This spiral feature in here, and this here, which is within the tidal thing. So the velocity map is not it shows, you know, the first order, I guess, a weak spider diagram across, but it has like a zero velocity line. It does a wiggle, like a Pepsi sign, right? And it's pulled by this arm here. We think this is tidal. It actually lies above the galaxy. And out there, this is some weird stuff going on with very high velocity dispersion curve.
Like naive question. So this has a higher sort of difference in velocity than Gauss usually, but
Yeah.
in your previous plots you had velocity over dispersion and it showed like this trend. Is there a velocity trend? Like do the redshift, the keep mass constant, is there a velocity like difference trend?
Yes.
Velocity curve?
Yes.
So this
Yeah, this is a high velocity. It's a very unusual galaxy with a very high velocity at high redshift. There's a lot of scatter in that plot. So this is one that I looked at that plot. It could fit in there, but it is, the universe gives us a ton of scatter. That was more averages. For this program, I did go for very bright galaxies. So they tend to be more oddballs, more psychedelic objects.
is this because the galaxies are more compact and higher range?
I don't know why this one rotates that fast. I am not sure. My gut feeling, and we should talk more, is that this is a merger remnant and it just got it from orbital rotation. There is an outer isophotal twist here, so I mean, naively we thought, oh, well, how are we gonna correct this? And it's like 35 degrees on the, according to the, you know, and so the correction to face on makes it rotate like crazy. There must be tons of dark matter. And then we looked at the outer isophotes, we saw this twist, and we're like, oh, that's nonsense. You gotta be careful with that. Got excited for a while. Another thing we noticed is that there's some weirdness in the spectrum. There seems to be a broad component in there. So what we did is we co-added all these spaxels to get higher signals to noise, one on one side of the galaxy, one on the other. And lo and behold, on one side of the galaxy, on this bit here, we get this. I want you to just look at the black line here. And then on this side, you get this. And you notice the black line, which is the spectrum that's co-added from all these spaxels, has like a tail on this side. And then it has a tail on this side. It's normally interpreted when it has a tail here as a wind on the other side. It's outgoing wind, hot wind from the galaxy, gas flowing out. Here it's like accretion. But it's odd that it's on one side of the galaxy would be accretion, the other side there'd be wind. It's like, nope. So we decided to just kind of look at it all over the galaxy. And again, we're binning to get higher signal to noise. So Celia binned this galaxy into these bins. And then lo and behold, finds that there's this thick component, the broad Gaussian and the narrow Gaussian are doing similar stuff. So this is spaxel by spaxel. It's drawn mostly by the FITS draw is 99% the thin disk. The thin component of slip. This is the broad component fit to H alpha. It also rotates. And this is the thin component, which is very similar to this. So it looks like there's a thick disk in this system. At redshift is 10 billion years ago, which is a mature thing that we see in local galaxies already in place at 10 billion years ago. Velocity of the thick disk, velocity of the thin. You see a deviation on either side. It's about 50 kilometers per second. There's a lag. Kind of neat. We were about to write up the paper and we found this. She's like, no. But then we were so happy we did. Because it just keeps giving. This is the broad and narrow components on the velocity dispersion. And you see the thick one is thicker. Well, yeah, by definition, there's an I in here I left out, sorry. And here's the thinner one. They both have higher velocity dispersions than local galaxies. So this is the number of galaxies versus lag. Celia made this plot by going very carefully through the literature. This nebulae stars for reference, edge on, face on, different ways of measuring the thickness. And so our lag is, the lag for this redshift 2 galaxy is higher than most lags locally, but still within the ballpark. Velocity dispersion of the broad versus the narrow, we're way up here, and these guys are way down here. These are the narrow ones. The lines are narrow from large surveys. So way out there. So please help us, Kirk and students, understand what this is. Is it an earlier stage in the thick disk? Do they then decrease in lag and settle? Like, is there thick disk settling too, along with the thin disk? We don't know. We just found this. Celia is now studying this for her thesis. So there's another galaxy. We studied the coffee pot with Ezra. This is the beauty of the NIRCam image. We call it the coffee pot because it looks like a coffee pot. It also is an easy way of remembering rather than a call number. We talk about it. Here is an H alpha map. So I'm putting these lines in here to show you the extent of the slitlet stepping. And then because I'm an observer, I drew a spirally. I said, okay, looks like a bar with 2 spiral arms, maybe not, but there's a lot of clumps in that H alpha image, a lot of star formation. Here's that velocity map. And you know, there is angular momentum, there is overall sense of rotation, but it is modeled and it is wacky. There's a lot of excursions in here. This guy here is like doing something, it's going way away from us. And a bunch of stuff here is really coming toward us. What's incredibly beautiful is this velocity dispersion map. I love it. And I really kudos goes to Jane and Mike and Addie and the students for iterating until these were just pushing past a lot of the artifacts and working out all the eccentricities of Webb. And so a beautiful increased velocity dispersion in the inter-arm region. We think there's probably another arm out here. We don't even see in the image that's pushing on this stuff. And then in this region down in here, with the dust enshrouded region. So here is a breast frame 3000 UV image, or feed UV. And then here is the zoom in. I'm sorry, and you see this stuff just kind of takes over that galaxy, and the clumps of star formation tend to form in the low velocity dispersion areas. This is what we had before from the ground. So from the ground, we were able to get to first order. You know, this makes sense with what we're seeing, but the interpretation was from some folks was that it was a rotating disk. You got to be very careful with that because it is not a rotating disk. That's a rotating disk. This is very, very different than that. Yes.
Do you also see the broad components in the bright regions as well, but they're just overwhelmed by narrower components that are in the bright regions, or have you been able to detect or constrain that?
We need to do that yet. Thank you. Yeah, I think we need to look into that very carefully. Yeah, that's been on our list. I think Ezra looked into first order, we like zoomed in and it wasn't there, but we have yet to really peel through it and start combining spaxels. Like, do you see it there? Yeah. What's interesting is you see a lot of this orange kind of goes around, it traces features in the image, which is really cool. So it makes me think that maybe there might be some more in there, but I think we're getting it. But I really want to start combining spaxels until I say for sure that it's there. I put Ezra on fitting galaxy winds after that, so he got busy. Yes.
Oh yeah, I should have asked before. So what's the physical scale here?
Oh gosh, there's this is half an arc second, like about 4 kiloparsecs, 4.5 for a change, 4.2 kiloparsecs. It's small. Yes.
I have a question. Why is the peak of the velocity dispersion there instead of near the?
Oh, because it's not a disk. So in the nucleus, you would see a rise due to the rotation curve. Right, so you in it, let me pull out the galaxy disk, right? That. If I was to blur this guy, I'm gonna see, if I blur these two, according to like seeing, you know, make it look like it's ground based, I would get a similar thing here, but I would see a rise here just because I'm blurring these velocities together. We see a rise, you know, in the inner part of the rotation where we do see a bit of that, but this is because it's due to something else. It's not due to a rise in the rotation curve. It's due to perhaps something like shocks.
We don't know what causes that yet.
Correct. So when you observe that rise, it's artificial when you get a bump in the center of a velocity dispersion map. It's just, you have to take that out when you model the seeing and you fit it. Yeah.
Excuse me,
Yes.
do you have like, emission line diagnostics? For example, like, some line ratios?
We
to-
do, we have H alpha and N2 and it may be shocks. I have yet to look very carefully at it though. I think it's shocks.
Uh-huh. Yeah, it looks like DIG, diffuse ionized scale,
It might,
because I think there's like, HR flux is like very low and looks like diffuse, especially compared to like 3000 astro. Yeah, continue.
maybe,
Yeah.
maybe. We should have a look at the spectrum there and just compare it to where we haven't had a chance to do that yet. So all this is unpublished. I apologize. It's not dotted, the I's are not dotted, the T's are not crossed, but that's exactly what we should do. Yeah, it might be dig too. So this galaxy has sodium D absorption. It requires sodium D requires dust shielding, so it happens in a lot of dusty galaxies. This guy has a lot of dust. And Ezra, we actually semi-resolving it here, and Ezra drew these little circles to get little regions where we have enough signal to noise to study sodium D absorption, which is amazing that Webb allows us to do absorption at redshift 2. And this is, so he measured the, you have to model out the stellar contribution. We did all that, and he gets an outflow velocity of about 200 for most of these regions. And if the outflow was coming from these individual regions, one would expect it correlated with the star formation rate surface density of those regions. It's not. So it looks like the outflow might be coming from one of these regions around the galaxy. We're just seeing it like it's like a cone pointed at, and we're seeing it obliquely. But we have to fully understand what is going on. We'd love to get your input on this. For me, it was surprising to find a velocity of 200. I was like, wow, we supposed to, according to these feedbacks, we should be like 500. No, 200. Yeah, so similar to local ULERCs, not that far off. Interesting. So now I'm going to slow down even more because this is stuff that it has, the plots even have some problems. Because our dither pattern wasn't exactly what I thought it was because I read the documentation wrong or the documentation was wrong, I don't remember. So we're going to take 3 galaxies and you're going to have fun with me, and they're between redshifts 3 and 5. So we're looking at like, I don't know, 12 billion years ago. And what's nice about these is they're single step objects. And I love that because we spent 60 hours on source. So there could still be some stuff hidden in the reductions. I'd not be surprised. And so hold on, I'm about to show you a ton of plots at once, but I will walk you through it. So this galaxy, we're gonna go up in redshift. Redshift 3, 60 hours on source. There's something going on with the center step in here. I think our dithers did not quite overlap. I thought they would, they didn't, whatever. Here is the galaxy in the near cam color images, multi-bands. Here it is in the J band. This is the reddest band on near cam, which is approximately rest J band. So it's 2 clubs. So these clubs across the top are reproduced below with the contours for this guy. Flux of H alpha. Lag signal to noise, probably some progress. Velocity dispersion. So I think the ones to look at are these down here, but I wanted to show you everything so, you don't feel like you're being hoodwinked, like, oh, this is just low signal to noise, what are you doing? And so here we have these 2 stellar clumps and this velocity structure, and this is minus 60, this is plus about 25. So talk to me. Are they probably not even virialized? they're not like going around each other. It's not like orbital where they're just going like this, right? They might be starting that though. And then we go out beyond this and we start seeing there's more gas down here. This is gas. And then there's this something going on here. We have very high velocity dispersion and then low velocity dispersion here. So this is why I'm here, to work to entice the theorists like you.
Do we,
Then, yeah,
do we have an estimation of the mass ratio between the two clones?
I can get you that, but not right now. But I think if you take the J band as essentially the mass, the one on the right looks maybe 1.5 times the one on the left.
Yeah, can it be like one, this kind of flyby?
Yeah.
In the side of side?
I think so.
Rotation.
That could be. Yeah, the other one could be flying by faster. You're right. Yeah. But this one is still move. It also we can move the 0 point of that velocity around too. Yeah. So yeah, it'd be nice to know what the scenarios are for this and whether we can constrain anything from these data.
How do you decide what the 0 point is? Let me
The middle.
That's fair, that's fair.
I said Celia when she made it, just be a stupid astronomer.
What is the signal to noise ratio of the, like the darkest spectral in?
7.
Seven.
7 is we did a cut at 7 to be
Uh-huh.
conservative, so we're not obviously not showing you any crap. We can go out further, of course. And then we're gonna start combining spectrals as we go out.
Uh-huh.
But you can see it falls up real fast.
Mhm. Yeah.
Kind of a tip of the iceberg scenario where we're seeing some bright stuff and it gets faint underneath. I can, you know, I'll show you big, like you've seen Kirk's and his groups, your simulations. And you see there's a lot going on that's faint hanging around there. You probably could show me that. Yes,
Seems like the 0 is pretty significant issue, right? I mean, you don't have an independent measure of the distance. So how do you know the peculiar velocity of the midpoint?
it may not even be virialized. It may not even have a center. We don't know. But we may be able to get statistically from your simulations at a redshift of 3, maybe there's always a center, and maybe it's always the first order 90% near the center.
There always sees a center of mass. Right?
Is there?
There's always a center of mass, it's not always a center of gravity.
Sure.
And is there ways that we can tell that when it's off? Yeah, we know there's a gradient, but yeah, we don't know where that 0 point is. It could be that the 0 point is way out here. Probably not, because it's not where the mass is, but who knows? We have to go in with some prior and say, if the mass is somewhat near the 0 point, we're gonna pick a number.
Mhm.
But it might be wrong. I agree. I mean, look at this. It looks like a jack. I mean, who knows what is going on? Or, you know, you can blur anything and get that, right? I'm not easily fooled by this. I know we're flying blind, seeing part of the output. Here's a one at redshift 3.8, another 60 hours on source. So we're getting all kinds of weird stuff in the outer parts. Color image 444. You still see two kind of clumsy. They're kind of melting together with this PSF. 444 is a fatter PSF. Kind of closer to our data. Let's go over here. There's a velocity gradient across it, which is kind of neat to always kind of see angular momentum in these systems. I mean, a lot of people at higher redshift are like, oh my god, disks. I don't think it's all disks. I think, you know, when you go deeper, you start seeing craziness all around. I think it's interesting that there's almost always angular momentum. That tells you about something about the accretion, I guess. I'm not sure. You guys have to tell me. And then if you go further out, Celia combined this just to get higher signal to noise, and it is indeed moving at 70 kilometers per second. And then this is the velocity dispersion. The stars are here, but there's a whole bunch of stuff going on here we've yet to understand. So we're kind of hitting this magic area where, you know, the IGM of the galaxy is here, and we're kind of moving out into the CGM, maybe starting to get a sense, because you have the inflow, it hits the CGM, then you hit the IGM. We're starting to get this interface in the observations. And we're seeing kind of a hot mess out there. I mean, these shocks, I'm making this up, this is 100, no, 160, 170 kilometers per second out here. It's bad. Something's going on. I love this one. This is redshift 4.7. These reductions, there's something a little funny with the middle bit. I don't know what that is. So ignore the middle row because something's gone crazy. I don't know what's going on with this middle row. But I want to show you my 31 tree. Why not? Get there. Oh, something's weird. But you can see, like, we see an artifact. We go back to the drawing board. What could it be? We iterate. We go back to different older stages, older reductions of the data. Up through it. And with this one, the stars don't even seem to know about what the gas is doing. They're just kind of here. Because I don't know. But the gas is like, oh my God, 50 here, 50, there's a 25 here and another 50 here, all 50 here. It's just this wild mess in there. There's this whole swath here of higher velocity dispersion. Again, ignore those two hot bits in there. I don't know what they are. So I've said it again and again. This is Kirk's work at much higher redshift. So he simulates galaxies in the distant universe, the first galaxies. And this is a native, so this is the density map, showing your own research. Your galaxy at redshift 9, you see there's cold flows kind of feeding it, tremendous amounts of structure, it's spinning, some angular momentum obviously in there. Here's a 1500 angstrom image of that at the native resolution of the simulation. And I slice and dice your figure. There's a lot more in the figure. Here it is at redshift 9 with the near cam image. You can see it's pixelized, but you're still getting a lot of the picture in there, showing that this is possible. I mean, at redshift 9, things are worse than at our redshifts, but you really need these mock observations to get a sense of what you're measuring, what you can and cannot constrain. Yeah.
Maybe this is a question more for Kirk, but where's the center of mass of the stars relative to the peak of the brightness?
In this particular galaxy, I don't know anymore.
Right, but okay.
Yeah, so, I mean, you're just thinking about the offsets between, yeah. I think, after talking to Susan quite a bit, I think a more detailed look into these irregular galaxies, very much more interesting. I think there's a big question mark, and but all the data is there. There's so many simulations of high redshift because that's where the simulations start. But I think it's time to combine the synthetic images with the kinematics. Think about this.
Because the timescales would obviously be a lot smaller than for galaxy clusters, but you should expect to see like bullet cluster like behavior, right? With offsets between the mass and the gas.
Maybe bringing stuff.
I would also say too, like, and Susan could correct me, but we see a lot of really strong star formation that comes in these clumps, right? And so when we look at these maps and we see the stars, like these are, here's one collapse of electric cloud, and here's another one over there. And yes, that's a lot of the brightness, but is it a lot of the mass? Yeah.
Absolutely. Good point. So this is why I'm here. So back to our questions. When do disks obtain their current well-ordered state? What is the dynamical state of galaxies in the distant universe? Come back to our little diagram. This is throwaway language. It's only now just assembly. Maybe they're not all assembling. Maybe they're not all virialized. We don't know for sure. We will hopefully figure it out. The CGM seems to show this complex kinematic structure. Maybe merging, maybe tidal features, shock secretion, who knows, but stuff is going on, and it's very complex. Around this area, around redshifts like 2, 1, really start them, you see them starting to settle and form mature structures, like these thick and thin disks, bars, spiral arms. And then between redshift 1 and now we call that the epoch of dissettling, where you have the spin up. So I think we're really we laid down the gauntlet with the dissettling, and he said, model this. And now they're busy modeling that. We now want to lay down the gauntlet at higher redshift and say, assemble this, make this happen. So we hope to garner the interest of folks. So, and then the other conclusions are the kind of first, the redshift 2, thick and thin gaseous disk. It's surprising because I didn't expect to see a thick disk at such a distant part of the universe. Is it a mature structure? Maybe it's something that is easily formed. Amazing. And then this kind of semi-resolution of this gas, of this, sorry, this gaseous outflow. I was surprised at 200 kilometers per second outflow. Like I thought maybe this would be huge. Nope. And it's maybe, maybe it's coming from, it's just like in a local ULR coming from one area and you're seeing the edge of that cone. And over to you for questions.
A lot of wonderful questions. I think we have more.
Yeah, you mentioned for some of the systems, you can even measure like the neutral gas outflows. What about the stellar continuum? Do you like confirm like the rotational velocity or those kind of stuff from stellar continuum?
So not from the continuum, but you're going to want to measure absorption lines
Yes.
and put the continuum at the same time. So you got to get the magical redshift range where you have the lines in your spectrum. So for some galaxies, yeah, we have like a calcium triplet that we're fitting. But for others, like for the bear claw, we don't. It landed somewhere on the detector gap or off the detector, so that was a little sad. But yeah, we do have some stellar features. The whole main goal of this program was to get that continuum. I mean, our continuum is not perfect. And then also we had to subtract the zodiacal light really well, and that's where Eddie Bergeron's work came in. We had some tricks for subtracting that off because that was our limiting source. Now we're read noise limited, which is, I can't believe it. Yeah.
Any other questions?
Yeah, just a basic thing, and you probably said this and I missed it, but so it looks like for all these objects, there's rotation, so you suggested they're rotationally supported. So can you say something about the mass?
I don't know if these are all rotationally supported. You mean these little guys?
Yeah,
I could naively measure a mass from
Yeah.
this, but I don't know if it's visualized. I don't know
yeah,
if that
sure,
would be.
sure, fair enough.
I
Fair
think
enough.
people do this,
Yeah.
and it's been done, and they've measured a mass, and then they've inferred a lot of dark matter because these things also
I
have a lot of gas.
I see.
I'm not willing to take those
Fair enough.
assumptions
Okay,
because I think it's one could, and we eventually will get there once we have like alma
Yeah,
for these
yeah.
guys. But I think it's more interesting to know whether it is a visualized system or
sure,
not.
sure, right.
And I think we will be playing the game of, are we getting the same mass if we, do the dynamics right on this as we get from the photometry, or at
Yeah,
least in the
I got
ballpark.
you, I got you.
But the errors on that are pretty large, but I think that's where we're going. We're gonna play that game. And then looking at the dynamics of systems to measure, say, dark matter. It's harder at higher redshift because they are more dynamically unstable, and especially when you go into the outer parts. I hate to be the naysayer. We're trying for it though. But like with that galaxy with Celia, with the Bear Claw galaxy, we're like, all right, perfect dark matter measurement, beautiful. Boop. Oh, outer isophoto twist. Oh, looks like a minor merger out there. Damn. So I'm very suspicious of a lot of those papers where they measure stuff, especially offhandedly. It's tough going.
Yeah, I got your point taken.
Yeah. Yes. Oh, you haven't asked yet. Please.
Maybe it's not really related to the dynamics, but there is a galaxy where you were mentioning that you detect some background with it. It wasn't the first galaxies you showed.
This one?
No, even maybe this one.
Maybe it's this one.
Yeah.
Background.
No, I think it's before that. In the first ones.
What do you mean by background? You mean like CGM or?
Yes, you.
I'm sorry. I misspoke. It was these guys, these two, where we're going out. So the galaxy ends here. And you're going out like more than another galaxy length further out. And I'm calling that CGM. Yeah, that's what I mean by background. And it could, yeah. I don't know if it's ionized by the galaxy or the UV background. I haven't done the calculation.
That's my question.
Yeah.
We'll just do one or two more questions then.
So in the beginning, you said the Guardian survey has 56 galaxies, right? So we have 5 right now, or more coming up, or?
Yeah,
Okay,
we're a small team, but yeah.
yeah, because I'm curious, like it's a larger sample size, I wonder if you see any kind of trend in the.
Yeah, and we also have another survey called the wait for it, meadow survey, where we're doing this for hundreds of galaxies, chosen with photos used, so not all will be up the redshifts we wanted. So it was like redshifts 3 and 4. And for that, we're looking at, you might be interested with spin alignment with the cosmic web and kinematics. But I felt I wanted to go deep first, just to understand what I was gonna get at. Because you're putting slits on those galaxies, I'm like, they all look like those jacks and kind of commas, you know, it's all a hot mess. I'm like, this is bad. Yeah. Or exciting, yeah.
Okay, one last question. Okay.
Yeah, is there any like agent host galaxies in your sample?
Yeah. Do you want that?
It would be interesting, yeah.
We could talk. I don't have anyone working on the AGM yet. I've kept it close to the inner team because we found all kinds of offsets and weirdnesses, and we didn't want to give people like data to play with and do wrong science with. So I've been very conservative with not giving the data out, because literally we found offsets that the web didn't address, yeah.
So these AGN, right, are they based on like just nuclear imaging or like spectral lines, or is like there evidence of outflows?
Oh, we have a broad line guy in there. I haven't looked at outflows, but I mean, you just see a broad line guy, and then there's some where we have all the BPT lines that we can maybe figure things out on. Yeah. I'm sorry. I'm glad I spoke with Decker French today. Having a lot.
Okay, so let's thank our speaker one more time. So that generated a lot of questions, more than average, by the way. So happy to take people to dinner. We're gonna do dinner at 6 p.m. We haven't decided where yet, but we're definitely gonna be here 15 before the hour. So people are invited to join us for dinner if you want to have some more time for a second.